Welcome to lecture number 2 that is focused on static code analysis, which is one of the most important practices in the modern software engineering. First, we will be seeing how to gather useful data about the software for static code analysis. As the software systems grow larger and more complex, manually reviewing every line of code becomes nearly impossible. Developers need automated techniques that can inspect the source code, detect problems early, and enforce coding standards and help to maintain clean architecture. Static code analysis provides exactly that capability. So we will be exploring what static code analysis is and why it matters, and how it improves the software quality. First, let's see what is static code analysis. Static code analysis is the process of analyzing the source code without actually executing the program. Unlike dynamic analysis, where the software is executed and monitored during runtime, static analysis examines the structure, the syntax, the logic, and patterns within the code itself. The primary purpose of static code analysis is to identify the bugs and defects, security vulnerabilities, coding standard violations, performance issues, maintainability problems, duplicate code, dead or unused code, complex or risky sections of software. So it automatically scans the code base and generates the report that helps the developers to improve the software quality before deployment. This process is extremely valuable because detecting defects early in development is significantly cheaper and easier than fixing them after the software release. Let's explore the objectives of static code analysis. The main objectives include, first of all, improving the code quality. Static analysis helps the developers write cleaner and more maintainable code by identifying the poor coding practices and enforcing the standards. Second is detecting bugs early. Many software defects can be identified before the program is even executed. So early detection reduces the debugging effort and development costs. Third is enhancing the security. Static code analysis tools can identify the vulnerabilities such as null pointer dereferences, buffer overflows, maybe unsafe object handling, resource leaks, injection vulnerabilities. Fourth, increasing maintainability. Well-structured code is easier to understand, modify, and extend. Static analysis helps us to reduce the complexity and improve the readability. 5. Supporting team collaboration. By enforcing consistent coding standards, team can maintain uniform coding styles across the large projects. Static code analysis also helps us to gather important information about the software system. This information can support developers, the project managers, the quality assurance teams in understanding the health of the code base. The analysis can provide insight in a number of ways. Let's discuss them all. First, detecting the bugs and violations. One major use of static analysis is automated bug detection. Static analysis tools scan code patterns and identify the suspicious constructs that may lead to runtime failures. Common bugs detected are as shown on the screen, like there can be null pointer exceptions that occur when the code tries to use an object that has not been initialized. Then infinite loops that never terminate, causing the program to hang or crash. Uninitialized variables that are used before assigning a value, leading to unpredictable results. Incorrect object comparisons, using wrong comparison methods, for example reference instead of value comparison. Resource leaks, resources like files or connections not properly closed after use. Memory management problems, for example inefficient or incorrect memory usage causing the performance issues. Deadlocks, when two or more processes wait indefinitely for each other to release the resources. Unreachable code that never execute due to logic or maybe control flow errors. In addition to bugs, static code analysis also identify the coding standard violations. Coding standards are the rules that developers follow to maintain consistency across the project. For instance, incorrect naming convention, that is variable, class, or method names do not follow project naming rules, reducing the readability. Improper indentation, so poor spacing and alignment make the code difficult to read and understand. Missing comments, lack of explanations makes the complex logic harder for developers to maintain. Then excessive method length. So very long methods become very difficult to debug or test and modify. Unused imports, so imported libraries or packages that are never used create unnecessary clutter. Magic numbers, so hard-coded numeric values without any explanation reduces the code clarity and maintainability. Then improper handling of errors may hide problems and cause software failures. Enforcing coding standards improves the consistency and readability across development teams. Another important area is identifying performance-related problems. Although static analysis cannot measure runtime performance directly, but it can identify patterns commonly associated with inefficient software. Examples include inefficient loops, so loops that repeat unnecessary work and reduce the program speed; redundant object creation, creating objects repeatedly when reuse is possible, so this leads to wasting memory. For example, consider a loop that repeatedly creates unnecessary objects. So in this example, a new string object is created during every loop iteration, even though the same value could be reused. So this unnecessary project creation wastes the memory and processing time. A static analysis tool may recommend optimizing the code by reusing the objects or moving the object creation outside the loop. Then expensive method calls inside the loops, that is heavy computation inside loops slow down the execution. This is another common issue that involves expensive method calls inside loops. For example, you can see this for loop. So if list dot size is computationally expensive, repeatedly calling it inside the loop may reduce the performance. The improved version would store the size in a variable before the loop begins. Poor resource handling is another example. If the database connections or network sockets are not properly closed, system resources may become exhausted, reducing the application performance over the time. Excessive memory usage patterns that consume more memory than required, or synchronization bottlenecks, that is too much locking in the multi-threaded code, slows down the overall performance. So static analysis tools can also identify synchronization bottlenecks in multi-threaded applications. For example, excessive use of synchronized methods may slow down the concurrent systems because threads are forced to wait unnecessarily. Now let's see some common metrics. Static code analysis tools often generate quantitative metrics. These metrics provide measurable data about the software quality and helps the organizations to evaluate the project health objectively. Number one is error count. This is one simple metric, that is error count. This represents the total number of detected warnings, bugs, or violations within the code base. For example, if a project report shows 25 critical bugs, 40 warnings, 12 style violations, the development team immediately understands the current quality status of the project. Second is cyclomatic complexity. It measures how complex a method or a function is. Higher complexity usually means harder testing, higher bug probability, reduced maintainability. So cyclomatic complexity measures how complicated a method or a function is based on the number of decision points, such as if statements, loops, switch cases, logical conditions. Consider this following method. So this method contains multiple nested conditions, increasing the complexity. So higher complexity usually means more difficult testing, greater probability of bugs, and reduced readability, and eventually harder maintenance. Static analysis tools often warn developers when complexity exceeds the recommended limits, or you can say thresholds. Another useful metric is code duplication, that indicates the repeated code blocks. Suppose the same block of code appears in 10 different files. If developers later need to update that logic, they must modify all 10 copies, increasing the maintenance effort and the bug risk. Static analysis tools identify the duplicated code and encourage developers to refactor the reusable functionality into separate methods or classes. Then maintainability index. This represents how easy the code is to maintain. This index estimates how easy the software is to maintain based on factors like complexity, readability, and size. A higher maintainability index indicates cleaner and more maintainable code. Then technical debt. Technical debt is also commonly measured, so it represents the estimated effort required to fix quality problems in the software. For example, if static analysis reports indicate that fixing all issues would require 120 developer hours, that estimate becomes part of the project's technical debt measurement. These metrics also provide valuable insights into project health. Then commonly used files and hotspots. Static code analysis can help us to identify frequently modified or commonly used files. These files are often called the hotspots, critical modules, or you can say high risk components. Such files may contain many dependencies and experience frequent changes, generate repeated bugs, and impact multiple system modules. Understanding these hotspots helps teams to prioritize the testing, improve the architecture, allocate maintenance resources efficiently, and reduce future defects. For example, quality assurance teams may perform additional testing on hotspot modules because they have a higher probability of failure. In large enterprise systems, hotspot analysis becomes extremely important because it helps the teams to focus on areas that create the greatest maintenance and reliability risks. Therefore, static code analysis is not only useful for finding coding mistakes, but also for understanding how software evolves over the time and where the future problems are most likely to occur. Frequent changes do not always mean bad quality. A file may change often simply because it belongs to a core module or it contains maybe important business logic that many features depend on. However, static analysis and hotspot analysis treat frequent modifications as a possible warning sign because repeatedly changing the same file can indicate underlying design problems. For example, if a developer constantly modify one class to add unrelated features, fix the recurring bugs, or adjust the dependencies, it may suggest the high coupling, that is, too many components depend on it, or maybe poor modularity, lack of separation of concern, fragile design, and difficult maintenance. The important point is that change frequency alone is not enough. It must be analyzed together with other factors such as error concentration, complexity, number of bugs, dependency count. For instance, a payment processing module in an e-commerce system may frequently change because it is central to the application. So that is normal. But if the same module also has higher complexity, repeated bugs, and constant emergency fixes, then the frequent changes may indicate poor software quality. Hotspot analysis does not automatically label frequently modified files as bad. Instead, it helps the teams to identify the files that deserve closer inspection because they are important, risky, or potentially unstable. That brings us to the end of this session. So we explored static code analysis. Now let's shift our focus to another important cornerstone of the software engineering course, that is refactoring. So I'll see you in the next session.